Hello, this is Dr. Joe Trout from the physics program at Stockton University. And today we're going to talk about Chapter 5, the Forecaster's Toolbox. And we'll talk about some general tools that are useful for many different forecasting situations and how to benchmark forecasting methods and making forecast tasks simpler using transformations and adjustments and methods for checking whether a forecasting method has adequately utilized all the available information. And we'll do that by looking at the residuals. And also techniques for computing prediction intervals. So if we look at the process for producing forecast for a time series data, it can be broken down into a few steps. And this process looks an awful lot like our process for scientific observations or the scientific method. So the first thing we want to do is get the data and clean it up and organize it. And then we'll want to visualize the data. And after we look at the data, we can decide what would be a good model to use. Then we'll go ahead and estimate and evaluate our model, and then maybe go back and make some adjustments to the model, and then produce a forecast. So step one is to prepare the data in the correct format. So this process would involve loading in the data and identifying missing values and possibly filtering the time series and other pre-processing tasks that might need to be performed. Packages that are available are T-Sybil and other packages such as Tidyverse. And many models may have different data requirements. So for example, there may be models that require that there be no missing values or the series to be in some time order. For example, let's look at the GDP, or the gross domestic product, per capita over time. So we'll go ahead and load in our library, if you haven't done it already, for FPP3, and we'll set up a time series, GDPPC, and we're going to use the global economic data that's from a database that's available with FPP3, and we'll mutate it to be the GDP divided by the population. So it'll take the GDP value and divide by the population. Step two is to visualize the data. So we'll visualize is a really important step, as we've been saying ever since you became uh, data science students. And it allows the identification of some common patterns and will help you choose the appropriate model. So for example, we can look at this data, and I chose to look at the country of Italy, and this is the GDP per capita, or the GDP divided by the population. And it doesn't look like there's a strong seasonal effect. There definitely looks like there's a trend. So maybe that might be what we use to predict the future events or future values. Step three is to define the model, and there's many different time series models that can be used for forecasting. And in each chapter, more models will be presented. And we need to specify an appropriate model, which is essential for producing an appropriate forecast, of course. Models that are available in Fable are specified using the model functions, and each use a formula X versus Y interface, And the response variables are specified on the left-hand side of the formula, and the structure of the model is written on the right-hand side of the formula. So for example, we'll use the TSLM model, and we're going to have the GDP per capita, and we're going to use the trend part of the model. So our model function is TSLM. This is a time series linear model. And the response variable is the GDP per capita, and it's going to be modeled using the trend function. So the special functions used to define the model structure vary between models. So there should be special sections of the documentation for each model function which lists these special functions and how they're to be used. So we're going to fit our time series, which is the GDP per capita, and we're going to use a trend model, and we're going to use the trend function of TSLM to do it. So the next thing to do is train the model. So how we're going to do that is we'll take the historic data and use that to figure out the coefficients for the model. So then we'll check the model performance and evaluate it. And once the model has been fitted, we'll check how well it's performed on the data. And there are several diagnostic tools available to check the model's behavior and accuracy. And it's measures that allow there are even measures that allow one model to be compared against another model. So we'll talk more about this in later chapters. But the idea is that we could run several models and compare them to one another and see which one does the best. So we'll go ahead and produce our forecast, and let's see let's do it for 3 years. So we'll forecast H equals 3 years, and the country is Italy, and we'll go ahead and plot it. So here we see our prediction, and you may notice that there's a solid line here, that's our prediction, and it follows pretty much the linear trend of the data. We also see a dark blue area that's labeled as 80% and a lighter blue area that's labeled as 95%. So in the R time series, especially those involving forecasting, right, and using FPP3 or forecast or fable, the 80% and 90% 5% intervals are represented. So the 80% interval, there's 80% chance that the future observed values will fall within the shaded area. And at the 95% interval, there's 95% chance that the value will fall within the wider band. These are not just about the model parameters, but about the uncertainty in the forecasts themselves. So if you repeated the forecast many times with new data, 95% of the time, the actual values would fall into the 95% band, assuming that the model is good. So let's talk a little bit about some simple forecasting methods. So first we have the average method, and the average method just takes the average of all the historical data and it will become the prediction. So in this case, every prediction we make in the future will be equal to the average of the data we use to train the model or the historical data. For the day forecast, we simply set all the forecasts equal to their last observation. So whatever our last observation was, it will be our predicted value for however long we predict. There's also a seasonal variation. And in this case, what we're going to do is set our predicted out value equal to the month of the previous year's value. So for example, if we wanted to predict the value for the average temperature in June, we would use the value from last June's average temperature. So it shows an example of using this um, seasonal variation of our model. And you can see what's happening is it's using values from the previous um, year's observations. So the first thing we'll do is load the libraries. So tidyverse is needed, and tsymbol is needed, and fable, and readr, and um, lubridate, excuse me. And we'll go ahead and open up our file. So we'll set the file path equal to our file name. And in this case, we're using Argentina, data from Argentina. And we can go ahead and load in the values. And note that in this particular one, we skipped the first two lines because the first two lines were a header for the data field. And then we can convert the date to be the format that we need it to be. And then we can go ahead and filter the data and then go ahead and create our database, our data series, and then fit our data series, and then go ahead and plot it. There's also something called the drift method, and this is a variation where we use the drift or um, and the average change seen in the historical data. So we'll take our data from the last observation minus the data from the first observation or the previous observation, and we'll sum all these up, and then we'll divide by the number of observations minus 1 and times h. And in this case, t is the number of observations that we have. So here shows an example from your book where they were looking at quarterly beer production, and they took the data from the previous years and used it to train these three data. So if you notice, first off, we have the mean, and for this forecast, every value in the future will just be equal to the average of the historic data. And for the NAVAF, the next value will be equal to the last value, and it will become constant through the data series. And finally, for the seasonal, we'll use previous year's values to find out what the next year will be. The mean may not seem like a really reasonable model to use ever, but if you think about it, as we said, if the data is completely random, it'll do just as well as any other model. So in this case, we can set the training data. So we could break up our data, for instance, into two parts, a training set and a forecasted set. And we can use that to test our model. For now, we'll set the training data equal from 1992 to 2007. And we'll use the window function to create the training set. Then we can go ahead and plot our various methods and take a look and see how they did. So now let's talk about fitting the residuals and the values and the residuals. So for the fitted values, each observation in a time series can be forecast using all the previous observations. So the fitted values are the model's estimates for the actual values. And in a time series, we're going to represent them as y with, with a tilted hat on top of it. So we call it y hat, and t for the estimate of the time. And these values align with the observed data in the training set, and they're used to assess how well the model captures the patterns. We also have residuals, and the residuals are going to be the difference between the actual value and the fitted value. So in this case, we use E sub t, and it's equal to our actual value, y of t, minus our predicted value or our modeled value, and which is y hat t. And they represent the errors or the residuals made by the model on the training data. So ideal residuals are randomly scattered around zero and show no autocorrelation, and they have a constant variance. So when we look at the fitted values, really they're equal to the previous value plus some function. So for example, with the linear case, it was equal to the difference in the values divided by t minus 1. If we look at the fitted values, each observation in a time series can be forecast from all the previous values. And why we want to analyze the residuals is to verify some model assumptions. So is the model capturing the trend and the seasonality? And are the errors uncorrelated and unbiased? So this helps us detect outliers and structural breaks and model inadequacies. So each observation in the time series can be forecast using all the previous observations, and we're going to check the residual plots, and we'll look at the time plots, and they should look like white noise. And the autocorrelation plots should be close to zero. And a histogram should be approximate normality. So let's look at the residual diagnostics. So a good forecasting method will yield innovation residuals with the following property. The innovation residuals are uncorrelated. And if there are correlations between the innovation residuals, then there's some information left in the residuals that should be used for computing the data. So if the residuals don't look like white noise or random, then then there's some information there that could be used to help predict the future. The innovation residuals have a zero mean, and if they have a mean other than zero, then the forecasts are biased by the mean of those variables. In addition to these essential properties, it's also useful but not necessary for residuals to also have the following two properties. So the first is that they have a constant variance. And the second is that they are normally distributed. So here we see um, output of um, a plot of Google's daily closing prices in 2015. So this is 365 days of data and the closing price in 2015. And we're going to use the naive method to look at this. And we're also going to plot the residuals. So plotting the residuals, we can see these spikes that we should go back and look at and try to figure out why these spikes occurred and use them to help us figure out the model. But in essence, we can see that there doesn't seem to be any correlation between these. We'd have to test for it, of course, but it looks like they're pretty random. And we can go ahead and plot a histogram, and it should look pretty normal. And if we look for the residuals, it can help us spot some spikes in the data that might be of interest. By the way, we don't have to do these individually. There's a shortcut where we can just look at the residuals themselves. So if we use the model, excuse me, and go ahead and ask it to look at um, the time series residuals, it will plot the residuals as a function of time and look at the lag for the autocorrelation and also look at a histogram of the data. There's other tests that we can use whether the residuals from the time series will behave like white noise. And it detects the autocorrelation over multiple lags. And some of the common tests are the Young box test and the box Pierce test. So for the box Pierce test, what we're going to do is look at the autocorrelation for lag K and sum them all up and multiply by the number of observations. We're going to hypothesis. The hypothesis is HO that there's no correlation and the residuals are white noise, and H1 is that the residuals show an autocorrelation. And we go ahead and test these, use these test statistics. So Q is equal to N times N plus 2 times the sum of K equals 1 to H, and then look at the sample or autocorrelation at lag K. So in this case, rho sub K is the sample or autocorrelation at lag K, and N is the sample size, and H is the number of lags being tested. Again, larger values for Q suggest that the autocorrelation does not come from just a white noise series. So we'll use this on residuals after fitting the model, and we'll choose a lag H. A good example is 10, or use the square root of the number of points you have. And in R, we can use FPP3 and look at these correlations or these tests for the residuals. So high values, p-values, the residuals resemble white noise, and it's a good model fit. Low p-values suggest autocorrelation remains, And the limitations is that they're sensitive to your choice of lag H, and they assumes approximate normality of the residuals. So let's look at the distributional forecast and the prediction intervals. So what are prediction intervals? And a prediction interval provides a range within the future observations or expected to fall and a certain probability. And drifters from the confidence intervals, this differs from the confidence intervals, which estimate the uncertainty in the mean. And it's important in time series because the future data is inherently uncertain. So we don't want to predict too far into the future, and we want to come up with a good range in which the future observations will actually make sense. So here shows a couple of examples of prediction intervals and from a couple different models. So why are the prediction intervals important? Well, they quantify the forecast uncertainty, and they're useful for risk assessment and decision making and for resource allocations. And their applications are for weather forecasting, financial markets, and inventory control. So a prediction interval gives an interval within which we expect y of t to lie with some specified probability. So for example, assuming the forecast errors are normally distributed, a 95% prediction interval for an H-step forecast is our predicted value plus or minus 1.96 of the standard deviation. So for example, the general term is that yt of our predicted value plus or minus c times the standard deviation. And in this case, our percentage, if we look up our percentage, we can use the multiplier from table 5.1 to come up with our prediction interval. So for example, if we consider a forecast for the Google stock prices shown in figure 3.5, the last value of the observed series is 531.48. So the forecast of the next value is going to be 531.48. And the standard deviation of the residuals is given is 6.21. Hence, the 95% prediction interval for the next value will be 531.48 plus 1 or plus or minus 1.96 times 6.2. And this will give us a range of values, the lower value using minus the product of those two numbers, and the upper value using plus the plus sign. And similarly for the 80% prediction, we'll go ahead and look it up in the table, and it comes out to be 1.28, and we'll do the same thing. So in multi-step prediction intervals, the common feature of the prediction interval is that they increase as the length of the forecast horizon increases. So the further ahead we forecast, the more uncertainty is associated. So when constructing prediction intervals, right, we're going to look at some common methods. There's the analytical version of ARIMA, which we'll talk about in a couple of chapters. That prediction interval is based on the model assumptions, And the bootstrap method is simulating residuals to estimate the uncertainty. And the quintile regression is directly estimating quantities of the prediction distribution. So how to compute the prediction intervals? We can use an analytic method or a bootstrapping method or a quintile regression. So if you look for the benchmark methods, there are four benchmark methods, and it's possible to mathematically derive excuse me, the forecast standard deviation under the assumption of an uncorrelated residuals. And if the standard deviation from the predicted values denotes the standard deviation of the h-depth forecast distribution, and sigma hat is the residual standard deviation, then we can use the following expression. So for the mean forecasts, we get that the standard deviation will be equal to the standard deviation of the residuals times the square root of 1 plus 1 over t, where t is the number of, of values you have. And if we look at for the naive forecast, then sigma is equal to sigma times the square root of h. And for the seasonal, we have sigma is equal to sigma, the standard deviation of the residuals, times the square root of k plus 1, where k is the integer part of h minus 1 divided by m, and m is the seasonal period. And finally, for the drift forecast, we have sigma times the square root of h plus times 1 plus h over t. And of course, R will calculate all these for you. So for example, if we look at the Google prices and we look at the point forecast, and in this case, we were using the final value before our forecast, and we can go ahead and find out what the interval is for the 85%, or excuse me, the 80% and 95%. So the functions that output a forecast object, many functions including meanf, nav, and snav, and rwf, produce outputs in the forms of a forecast object, and the object is of the class forecast. So the following list shows all of the functions that produce forecasts that are available to you. And we'll talk about many of these in the chapters to come. We spoke back on chapter 2, I believe, about using transformations, and now we want to talk about forecasting using transformations. So there's some common transformations which can be used in modeling, and I'm sorry, they were discussed in section 3.1, not 2.1. And when forecasting from a model with transformations, first produce the forecast of the transformed data, then reverse the transformation or back transform to obtain the forecast on the original scale. So for the Box-Cox transformations given by 3.1, the reverse transformation is just to take the exponential of W1 if lambda is equal to 0, and take the sine times lambda times the WT plus 1 divided by lambda WT plus 1 raised to the 1 over lambda. The Fable package will automatically back transform the forecast whenever the transformation has been used in the model definition. So you won't have to exactly run on any of these equations, but this is what they're doing. And the back transform forecast is distributed, and then the transform normal is then a transform the normal distribution. So we could transform the data, then make predictions, and then transform back into the original scale. Let's talk about forecasting with decomposition. So in this case, we have a time series decomposition, which we talked about in chapter 3, that can be useful step in producing the forecast. So assuming that the additive decomposition, then we know the decomposed time series can be written as S of t plus A of t, where A is the trend plus the residual. So the actual data is equal to the seasonality or the seasonal component plus the trend plus the residual. Or if it's multiplicative decomposition has been used, then we can write that it's equal to S times A, where A is equal to the trend times the residual. So for example, if we look at the US employment data, and I'm going to look at how many people are employed by the government. So we can go ahead and decompose it into its three parts, and then we'll come up with the Nave seasonable adjusted forecast and auto plot and look at the number of people that are employed by the government. So here shows our prediction, and once again, we'll use the last value to predict the next value. When evaluating point forecast accuracy, right, we can look at the windows function, and the windows, and we already talked about this a little bit, we can set up a window of time for us to train the data, to train the model, or to forecast the model. Another useful function is subset, which allows for more types of subsetting. So it's a great advantage of this function is that it allows for use of indices to choose a subset. So for example, in this case, we could use the length of 4 times 5, which extracts the last 5 years of an observation, and it allows for extracting all values for a specific season. We could also use subset of our data quarter equals 1, which extracts the first quarter for all years. Or we could use tail, which are useful for extracting the first few or last few observations. Similar to when you use Linux or Unix, the tail function will tell you the last couple of lines of a file. So when we look at forecast errors, let's take a typical set as typically about 20% of the total data. So we'll have the training data, and then we'll have the test data. So once again, if we're going to use the model to predict the future, why not test it out? So let's say we have 10 years of data, right? Maybe we'll use 8 years to train the model and then predict the next 2 years and see how well our model does. So the test set should ideally be at least as large as the maximum forecast horizon. So note, a model which fits the training data really well may not necessarily forecast well, and a perfect fit can always be obtained by using a model with enough parameters. An overfitting of a model to data is just as bad as failing to identify systematic patterns in the data. So just because we can um, match the historical data perfectly doesn't mean that our model is going to do well in the future. So just as an aside, let's take a look at the population in Atlantic City, New Jersey. So if you've ever had a course in um, differential equations, you know that we can use a differential equation to model this data. And it looks like it's growing exponentially. So, and we're going to use a model to fit the data well, and it's not necessarily forecast well. So assume that the population depends on, assume that the population growth depends only on the population. So what I'm saying is if there's 10 people, they can only have so many babies in a year. And if you have 100 people, there's probably 10 times more babies that they can have per year, right? So the bigger the size of the population, the bigger the rate of growth can be. So in differential equations, we can say that the time rate change, that's dp dt, of the population, where p is the population, is just equal to some constant times the population. So the model I'm going to use to get to this data will just be the initial population times e to the kt. So what I'm saying is the population is growing exponentially. So, and P naught or P zero is the population at year zero. So in this case, it's in 1860, the population was 687 people. So if I wanted to fit this model, all I have to do is figure out what K is. And one way to do this is just to take a guess. So I'm going to take a guess and I'll play around with the numbers and I'm going to guess it's about that K is equal to 0.087. And once again, the raw data is in dots, the blue dots, and my model for the data is this blue line. So I don't know, just guessing at K, I did pretty good. I came up with a pretty good idea or a pretty good model. So what I'm saying is that the population in each year will equal the population at 1860 times E raised to the 0.087 times T. Well, I can do better than guess. I can use one of the values. So in this case, what I'll do is solve for K. So I'll divide both sides by the population, and I'm going to use some value, say 50 years. So at 50 years, that will be 1910, and the value there was 48,150. So I can use that to solve for K. Even a better method that we'll use sometimes, and you'll use it in chapters to come, is we'll take the log of both sides. So I'll take the log of K, in which case now my data becomes a straight line. And all I have to do is find the slope of this straight line, and that will tell me my value for K. So I'll go ahead and fit it. And it looks like it fits the data pretty well. So I'm going to use this to predict what happens in the future. By the way, we didn't have to really guess at any of this. If we take dp dt is equal to a constant times p, we'll use separation of variables, and you won't be tested on this, but you should see it. We'll use separation of variables. We'll divide through by p and multiply through by t, and then take the integral of that. The integral of 1 over p is just the natural log of p, and the integral of k is just a constant, so the integral of dt just becomes t, and we're left with the natural log of p minus the natural log of the population at time 0. And if you know anything about logarithms, ln p minus ln of p naught is equal to ln of p over p naught. And then we'll take the exponential of both sides and we come up with a solution. So now we have this great model and it works pretty well. So let's use it to predict the future. So all of a sudden we go ahead and try to predict the future, and our model just completely falls apart. So what we did was come up with this perfect model that fit this historic data, but when we tried to apply it and predict what's going to happen in the future, it completely fell apart. Well, as it turns out, there's a couple of reasons for this. In the 20s, tourism was at its peak, and during Prohibition, Atlantic City was not really good at enforcing Prohibition. And in 1930 to 1960s were the heyday of nightclub entertainment. However, after World War II, um, there was a lot of poverty and crime and corruption in Atlantic City. And also people realized now more people had cars and they could go to Atlantic City for the day and not have to stay there for a week. So the population started to decline. And then, of course, in 1976, they passed a referendum um, to legalize gambling and some things. None of our model took none of this into consideration. So even though we had this perfect model that fit the data, the historic data, it wasn't any good for predicting the future. And sometimes that's what happens. So if you make your model fit historical data perfectly, that's not to say it'll predict the future. But don't give up hope. It's still worth trying to predict the future, but remember, a model which perfectly fits the historical data, which is what that example we were just trying to show you, might not be the best predictor. And we'll talk more about this later. So how do we measure the success or failure of our predictions? Well, one way is that we'll look for the forecast uncertainties. So where the training data is given by y of t, right? So we have our error will be equal to the actual data minus our predicted data. So these residuals are calculated in the training set, while forecast errors are calculated on the test set. So the residuals are based on a one-step forecast, while the forecast errors can involve multiple steps. So what we're saying is, if we look for the residuals of our model, that's equal to our model fitted minus the actual training data minus our model, and we have broken up our data into two data sets, the training set and the test set. So, for example, for our um, Atlantic City data, if we looked at our year zero, that was our first year, and then 10 years later, and 20 years later, and 30 years later, and 40 years later, and 50 years later, and they were years 1860 through 1910. And here was the actual population, and here's the population of our model. And if I look at the actual error, that's just the population minus the model. So there's zero error the first time, and then for the next step, we have 1,000 minus 1,700, and so forth and so on. So if we look for the percent error, we'll divide through by the model, um, by the actual population. So we see if the percent error, we get about 63, and then about 23, and then about 20 and 7, and then about negative 38. So it's not doing really well. And if we were to keep doing this, we'd see that our percent error will get worse and worse as time goes on. And this usually happens. So as you forecast further into the future, you'll have more errors. So if we look at our scale dependent errors, we talk about the mean absolute error, and that's just the average of all the errors. So we take our actual data minus our model data and take the average of it. We use the absolute value because if not, we could have huge errors, but some of them are positive and some of them are negative. So when we take out the average, we get zero. So in this case, we'll take the absolute value of it. Or another way to do it is to take the root mean square of the error. So what we're going to do is take the error for each time step and square it, and then take the average, and then take the square root of the average. So if we look at the average error, we'll add up all the errors and divide by 6, and we come up with negative 2,115. And it looks like a lot, but it's only 13% of the actual average. If we look at the root mean square error, we'll add up all the errors squared and divide by 6. And we'll take the square root of this number, and it comes out to be 7,449. But once again, that's only about 0.5% of the average of the average of the average. Sorry, about 0.5% of the average population. They'll also talk about the mean absolute percentage error, which is the mean of PT, where PT is 100 times the error divided by the value at that point. This gives a heavy penalty on negative errors. So if we look at the mean absolute percent of error, or the MAPE, right, what we're going to do is we'll take the percent error. So we'll take the population minus our model, and then divide by the population, and we'll get these values, and the mean absolute percent error is about negative 8.62. And in this case, we'll get if we use the mean absolute percentage of error, we end up with about 25%. There's also the symmetric mean absolute percentage error, and we'll take the mean of 200 times the actual value minus our predicted value, divided by the absolute value plus, I'm sorry, let me try it again. We'll have the mean of 200 times the absolute value of the difference between the actual value and our predicted value, divided by the sum of our actual value plus our predicted value. What it really is what we're looking at is the average between these two values and the difference. So that's where that factor of 200 comes from. So our mean absolute percent error comes out to be about 22.69. And once again, what we did was we took 200 times the difference divided by the sum. And we took the absolute value of the difference. We can also look for non-seasonal time series. A useful way is defined as the scale the error uses MACE, which is the mean of Q, and Q is the error divided by 1 over t minus 1 times the sum from t equals 2 to t of the difference between the two values. By the way, all of these can be found using R. And for example, if we look at this example, we're looking at the window of from 1992 to 2007. And we're looking at the Australian Beer Company. And we'll look for the mean F and RWF and the seasonal version of NAVE. And we'll auto plot it and look at the values. So in this case, we had our test data. We had our training data back here, and this green line and this blue line and this orange line are our predictions using the various methods. And we saved some of the data to test it. So here's our test data, is also shown as this black line underneath. And here shows the values of the different error or analysis that we did on the difference between our model and the actual version. So all these things can be figured out by in R. You don't have to do them by hand or anything. And if we look at Google stock prices, right, we can find out, we can do the same thing. So we'll go ahead and look at the drift method, and the mean really doesn't do well at all. The nave doesn't seem to do horribly, and the drift method, and we can see what these errors are. So we can compare these three models all at once, and we see that for all of these, the mean did the worst in all of these measurements, right? And for the nave, it was pretty bad, but it was a lot better than the mean or the average method. And for the drift, that seemed to be doing the best so far. For example, three, had a made up database. This is thousands of units of refrigerators that are manufactured in a plant and the days that they took. So in this case, for some reason, they have a seasonality, but the seasonality isn't 1 year. It looks like it's about maybe 5 days. So we'll go ahead and load the libraries we need, and we'll load this test data, reefer units, time series, and it's a comma separated variable database or data file. And then we're going to rename the columns to day and units. And then we're going to ensure that there's enough data, and we need at least 250 rows, and we want 200 for training and 50 for testing. So we'll go ahead and set it up. We have the training unit defined, 1 through 200 points, and then the test data, 2,201 to 250 points, and then the test days are 2001 to 201 to 250. And we'll go ahead and fit the seasonal model to it, and we're going to use the trained data to train it, and then we're going to use it to forecast our values. And we'll plot the actual versus the forecast, and then we'll compute the accuracy of the model. So we have the accuracy of the model and the test data. Then we'll find those error analysis that we did. And we want to be careful because occasionally SMAPE will have, if it has a 0 in the denominator, it'll blow up. So we want to take care of that. So we go ahead and fit it. So we fit our data is in red, our forecast, and our actual data is in blue. And for our values, we had about 0.76 and about 1.039 and about 25 and 34. And it looks like it fit pretty well. Here's the adjusted gross pay, another example. And in this case, we use the mean and the nave and the drift, right? And once again, it looks like the drift did the best in this case. A more sophisticated version of training test sets is a time series cross-validation. And in this procedure, there's a series of test sets, each consisting of a single observation. So we use this much of the data to predict the first prediction, and then we use one more point to predict the next one, and we go ahead and just predict point by point. So unlike regular cross-validation, which randomly splits the data, time series cross-validation respects the temporal sequence and avoids training on future data, which can create what we call data leakage. So how this works is that the data is split into training and validation sets in a sequential model, and the model is trained on a time-ordered subset and then validated in the next step. And this process is repeated by moving forward in time, either with a rolling window of a fixed size or an expanding window with a growing size. So in this case, this plot shows that the forecast error increases as the forecast horizon increases, which isn't surprising. So the further we predict into the future, the more uncertain our prediction becomes. And here shows some of the error using this cross validation. Okay, thank you.